To start off the afternoon session, we have Jerry Stevens from IBM to talk about SMC-R. For those who don't know, you'll learn right away, but SMC-R is sort of a sockets implementation. I won't characterize it too much. I'll leave that to Jerry. But Jerry has spoken here before and introduced this topic in years gone by. I think it was last year, and is also a participant in the iBug workshop for the same reason. So, Jerry?
Okay, good afternoon, everyone. So I'm Jerry Stevens with the System Z IBM team in architecture and strategy, and I did discuss this topic last year and somewhat the previous year, and seems like the last 10 years, but nevertheless, it's been a while. And some of you may be familiar with it, and some of you are not. So here's basically what I'd like to do with my 30 minutes is give you a review of what SMC-R is. Hopefully that'll help set the foundation for most of you. Provide a status update of where we are with this, and give a little bit of glimpse of performance in terms of the solution, and then talk about where we are with the Linux piece of this. Okay, so going back a little bit, we're looking at this title of this solution. What's it about? What's the architecture, the model? Basically, it's to give the ability of two distinct compute nodes to share memory over an RDMA-capable fabric for the purposes of communications. And so logically, of course, they essentially have access to the same memory, logically, and it's the model is a producer-consumer model where the SYN socket semantics produce data into the peer's memory, and the peer consumes that data using normal socket semantics. And so the solution itself is documented on in an informational RFC, which you can find here, and I have more references in the back where you'll see additional information. If you go to that RFC, I would encourage you not to be too intimidated with the length of it. Just at least make it past the intro, and if you do make it past the intro, you'll send me an email. Maybe I'll buy you a cup of coffee next year. But it's not that bad. But the point is it explains some of the rationale. How did you get here? Why did you arrive at this? And basically what I described last year is why we're here. Sean and I discussed this together, and we discussed our sockets and this solution simultaneously for quite some time with help of Paul and Jim. And the discussion was about, could it be one solution? Does it need to be a separate solution? It's somewhat of a long discussion, but the bottom line is we needed solve problems that our sockets did not solve for us, and I'll describe those in a little bit. But at the end of the day, we arrived at different solutions, but certainly I think that both solutions could work for you in your environment depending on your needs. But in the enterprise space, our customer set is a little bit different. It's very similar to what was described by the VMware team. You'll see some of the same data center issues come up. Here I try to depict the architecture a little bit more detail in this case. So what you'll see here is that the way this protocol works is the TCP/IP connection sets up over the Ethernet fabric just as it does today. And the way it works is we've defined, working with the IETF, a new TCP option that's SMC-R. If both peers exchange that option, then we'll negotiate switching out of band to use RDMA. And what happens then is we will then exchange application data using RDMA semantics, and all of this is transparent to the application middleware. It's completely compatible with Sockets API in terms of all the requirements that socket applications expect, everything from the programming threading model to all the semantics of the various socket calls. So once again, we connect over IP, exchange the TCP option if both hosts are enabled for it. Then we will also proceed with the exchange of the rendezvous data, the RDMA semantics, to negotiate switching out of band. It's very similar to SSL, if you're familiar with that. In other words, the SSL handshake occurs in band in the TCP connection and may or may not use it. That's the way this protocol works as well. So this next chart goes into the details just a little bit lower. So here I'm showing two nodes, and this thing called OSA is the name of the adapter on System Z. It's just an Ethernet adapter. The adapters could be separate or physically the same. The architecture works either way, doesn't really matter. But the architecture does have the ability to resolve that issue. We could have multiple adapters, multiple Ethernet, multiple ROCEs. They'll logically group them together as necessary. But what you'll start noticing here is the model is that there's a parallel stack next to TCP. And using the normal socket family, we can switch into the SMC-R stack as necessary. It's a kernel solution. Many of the problems we had to solve required a kernel solution. You'll see that come up here in just a moment. And user space solutions just did not work for this customer set. Now, once again, I'll demonstrate that. But once again, the TCP/IP handshake occurs over your normal networking interface, and if that step 1 passes, which means both peers exchange this new TCP option, which is documented again in the RFC, then they'll proceed to the next step, and in band over the IP network, again, similar to SSL, we will then go to the next step, which is called this connection layer control, which is just another 3-way handshake to exchange RDMA credentials. And then if that step can be successful or it can fail. If it fails, we just fall back to IP. If it succeeds, then we'll set up a pipe. And the way this works for this solution is we set up a permanent pipe with permanent memory that backs these 2 peers, and we just map TCP connections on and off that memory and that pipe as needed. So that footprint is there, and the memory size, it can contract and expand as necessary. We can grow the pipe as necessary as the workloads come and go. And if TCP connections drop and stop using the pipe, then we'll drop those resources as it times out. But we try not to thrash, so we'll leave that pipe up as long as necessary, and that's tunable. But the point is that it's a permanent pipe, permanent memory. Applications exchange data in memory, and we allow the adapters to do all of the passing of the data. And then, of course, with socket semantics, if an application invokes a send API call, we simply give that to the adapter using RDMA writes and send message for control information. That then occurs over the reliably connected queue pairs that connect to 2 peers. Only the first connection sets up the queue pairs. After that, subsequent TCP connections come along. They use the same resources, and we can once again grow the memory if needed. But the intent is the memory is quite large, and it would map multiple connections across it. And typically, in our environment, we might see 50 to 60, maybe even 100 TCP connections between these 2 hosts. And it's, again, intended to be long-lived. Now, in addition to creating the reliably connected queue pair, in the architecture we refer to as link, and we also provided our own bonding, which we call link groups. And the notion is we can grow these out across different physical paths for both load balancing and high availability. And of course, resiliency is very important to this customer set. We cannot inject any single points of failure. In fact, it'll have double, triple, and resiliency methods. And in this case, I just show an example of 2 paths, but you could have more. And again, once again, we balance our connections across the physical paths. And of course, if we were to lose a path, either a switch or an RNIC, we have the ability to drop those connections and move them back and forth as necessary. Again, the applications are not participating. All of this is abstracted from the socket application. If that path is recovered, we would just move connections back to the recovered path. So this link group technology allows us to, again, once again, to grow the bandwidth and to provide resiliency across the network. Now, here's another problem that was very difficult for us to provide RDMA in our solution. We know that in data centers, and certainly at an enterprise level, there are many multi-tier workloads. In fact, most of the workloads are multi-tiers, and tiers can be 2, 3, 4, and 5 deep. So again, the chit-chat between the different servers within the data center is extensive. It's not the same as HPC, but it is extensive. So in order to finish one transaction, you might have hundreds of flows that occur within the data center to finish that single transaction. What sits between all these tiers is, traditionally, it's a TCP load balancer. The customer has a tremendous investment in these load balancers from all types of priorities and classes of services and moving servers around. And so any solution we provided would have to provide compatibility with the load balancers. And so the way this works is the TCP connection comes into a distributed VIPA, and that load balancer will pick the most suitable copy to distribute that work to. This is very common in customer data centers. There are all different variations of this. But IBM provides our own clustering, which is called Sysplex, and we have a distributor as well, and we have customers that use tiers of load balancers. But nevertheless, most of them are TCP connection oriented, and that load balancer has awareness of that TCP connection. This is not a firewall. It's a transparent hop on a flat layer 2 network. It's an IP subnet. But nevertheless, they'll pick. In this example, I picked this server instance on top to load balance this connection to, the distributed VIPA. And the tier in the middle isn't aware. This it just sees one IP address. It doesn't really know where it's going. But now I would like to be, in this example, if the 2 peers exchange the SMC-R option, we would go ahead with a negotiation and possibly set up an RDMA connection. And where this really becomes not only compatible, it becomes very powerful, is that with TCP/IP, all of the packets go through that load balancer, and load balancers have significant investments in accelerating that forwarding, and they're very optimized in terms of doing that, but they can become a bottleneck, as most of us know. But nevertheless, with this technology, if you connect, we can create a connection directly between the two peers using RDMA, the solution I described in the previous chart, and now all the application data flows bypasses the load balancer. And so not only is it compatible, the stress that's on the load balancer is removed because they communicate directly using the same Ethernet fabric. And of course, if he distributes this to a different host, of course, he can negotiate that connection as well. But this would require that the second tier and the third tier support SMC-R. And once again, this client that's initiated this transaction, in order to finish it, there could be many flows between the tiers, and there could be 3 and 4 tier deeps to finish the single transaction. And once again, any solution that we provided in this space would have to meet this requirement. And so the TCP load balancer was very important for us. So just a quick overview of everything I just said is that what this thing does is it basically is a hybrid solution in the sense that it still depends on the TCP/IP and your IP infrastructure. Our customers have an enormous investment in their IP infrastructure, primarily in things like IP security, IP filters, intrusion detection, encryption, SSL typically, and authentication. And to tell them that you would move away from that and replace those with something else is very disruptive. So nevertheless, the hybrid nature of it says you can keep all that operational administration functionality in place, and you can use this solution when you exchange data. Again, RDMA, we keep the connection. TCP connection is the connection manager, if you will. If you were to drop the TCP connection, we would drop the RDMA connection. If you would change an IP filter while it's active, we'd drop the RDMA connection again. So anything that disrupts the TCP connection would disrupt the RDMA connection. It basically becomes your control point. Again, it uses standard TCP/IP three-way handshake. We added a TCP option. Each endpoint exchanges their options within the rendezvous. If we get past that first step, then we have a new three-way handshake to exchange RDMA credentials. If that fails, we fall back to IP. If it succeeds, we will then use RDMA. Again, the socket application is unaware of this. It's just enabled in the host, and it basically is we, again, maintain socket semantics in the programming threading model of the application. And that's, if we have found an issue, we've been testing this for 2 or 3 years, then of course we would address that issue. But again, the intent is that it would be fully compatible. Again, the TCP connection remains active for the life of this. If it were to drop, we would drop the RDMA connection. Some load balancers are very sensitive to this fact. In fact, if they don't see activity, they will drop the connection. So we have the ability to send keep alive over the IP network if necessary. That's configurable. And that would keep a load balancer happy. Every so many minutes, we'd send a keep alive, a traditional TCP keep alive, or an IP packet. And we also have the ability to ping the reliably connected Q-pair fabric if there's no activity as well. We only do that again if it goes quiet. And again, if we have persistent TCP connections that stop exchanging data, we would ping the reliably connected Q-pair as well, as necessary. Again, this model, it preserves most of the vast majority of the critical existing operational considerations that are required by our customers in the way of security, load balancers, and their IP topology. So one key point of the IP topology, you do not need to change your networks, your IP subnets, or provision new IP addresses or change your IP topology in any way for that matter. So to summarize that, so the question is yes, what's the problem you're trying to solve? We're trying to provide better performance. Performance means different things to different people, but certainly it means latency, throughput, and scalability, use of CPU resources. And we all realize that RDMA technology allows you to do that. It needs to be transparent to the application middleware. So what does an application have to do to turn this on? And there's nothing there. So basically, each OS could control that differently in terms of their implementation. And on our operating system in ZOS and System Z, it's just a single global configuration option. You can turn it on, you get it for anyone that exchanged the SMC-R option. You can control it on an IP subnet. I like this IP subnet to use it and this IP subnet not to use it. So there are some granularity controls if you needed that. Again, it leverages existing your Ethernet infrastructure. So once again, you do not change your middleware. You do not change your hardware in terms of your networking hardware. You do need to have HCAs that are RDMA capable, of course. But again, our solution is 10 gigabit, and again, but it's just based off of ROCE. This next bullet is very important. Once again, it must preserve the existing security model. So once again, our customers will require that, once the IP filters, intrusion detection, authentication, encryption. Now, it is not compatible with IPsec, of course, because there's no IP packets. Again, the way this works, once we get into the exchanging of data, there are no packets at all. We directly write and read. Socket send, if he sends 1,000 bytes, we write 1,000 bytes. As is. We never packetize anything in the solution. So we have a different stack that's in the kernel, if you will, but it's not TCP/IP. We completely bypass the TCP/IP stack using this model. In terms of resiliency, again, we cannot inject any single points of failure. So if we lose a path or an adapter, we have the ability to move those connections and workloads over to the other path. If that path comes back, we will load balance back to provide the balancing the loads across the adapters. And then finally, once again, there's no provisioning of IP networks or IP addresses. It uses your existing TCP/IP network. So that's a summary of what SMC-R is. And I'm going to go into the next topic to talk about our status. But before I do, I'll just see if there are any questions, because it may not make sense to you if I'll just take a, yes?
So what about, I know it's not using TCP/IP, but what about applications, legacy applications like through TCP options? Like NAGLE, disable NAGLE, no delay, or things like that.
Right. So the question is what about other TCP/IP options that control performance, like enable and delay act and some of these other aspects? So basically what it amounts to is that anything that the application passes, we just tolerate, and we'll but fundamentally it doesn't affect the transfer of data. There's nothing the application can touch or do to affect what SMC-R does, because essentially SMC-R, if you issue a socket send, we write it, and we have the ability to all those same problems are there, don't get me wrong, but in terms of mapping the TCP protocol to this protocol, it's not necessarily one-to-one, but we have the ability to optimize acknowledgments or eliminate acknowledgments, but in terms of the application controlling it, they don't have a need to do that. So we wouldn't post an error. We just tolerate anything they give us. You want NAGLE, you got it. You want delay act, you got it. Yes?
Does this allow the use of shared memory across many systems? I mean, the same memory space would be shared across many systems.
Right. So let me just repeat the question. So that it's a great question, because I showed a point-to-point model here. But does it allow you to share? So when I create a buffer to share on this model, I'm sharing that memory space with one and only one peer. If I have another peer that I want to use this solution to, I would allocate and provision a different piece of memory space for that other peer. So every peer has its own memory space. In fact, we'll even break those up by virtual network. So if I'm talking to the same client-server model and it's on a different virtual network, a VLAN, we will move that all over to a different memory set to isolate the two workloads from each other. But the short answer is every peer-to-peer connection gets its own memory set. And we can grow that memory set and contract it as the workloads come and go. For 16 connections, we'll have a smaller amount. For 100 connections, we'll have a larger. And as they go away, we'll contract the space. But it is specific to every point-to-point connection. Yes?
I actually have two questions. First is, why a TCP option? What is it about TCP and the TCP option that enables your protocol? Aren't there any alternative solutions?
Okay. Question one is, why TCP option? Why'd you do that? And the answer is that, again, we looked at the solution. So first of all, we felt like for our workloads, for enterprise, business, commercial space, the predominant workload was TCP based. Now that doesn't mean you got that, but then so what we wanted to do next was to be able to provide the solution that said this is a TCP-like attribute, and we, in order to go to that next handshake, we need to know if both peers, something in the TCP/IP handshake, to tell us to proceed. And so that could have been an IP option, it could have been a TCP option, but we believed it fit best in TCP. And believe me, we studied to death. I went to the IETF, had a much bigger discussion on this.
Okay, good. Question number 2, why Rocky? What is it about Rocky that's important?
Okay, so why Rocky is the question. So for our customers, for the vast majority of them, Rocky provides IB-like transport in an Ethernet environment. It's pervasive. It's basically a way of telling our customers, different set than HPC, a little bit different problems. It's not necessarily scientific. It's typically financial, business, and it's basically a business question. This is the vast majority of them. So now we have a solution that says you don't have to change your network hardware or your software, and here's the performance you get. And then customers will still look at that and scrutinize it. They'll still say, I don't know. I don't have to change anything. I don't like that. I need to change something. So the point is we're saying, how can we get into your space the easiest? We might go to the other fabrics in the future if customers like the solution, but the intent is no software changes, no hardware changes.
All right, that was my third question. So there's nothing about your protocol that precludes use of other RDMA?
Nothing about the protocol that would preclude us from using the others. If the business case gets there, we'll get there as well. Right now it's Rocky. It's focused on just Rocky on the platform. Yes?
Why are we calling it shared memory? It's basically data transfer, right?
And why are we calling it shared memory? Yeah, so that's a good question, so basically what we found is we created a solution that out of necessity because there wasn't a solution that met our needs. But the logical premise of this is that the buffers that I showed in that first page, that view from the 40,000 foot level, is logically that both those applications are sharing the same buffer for communications. Now, shared memory means different things to different platforms. In this environment, it means that two distinct compute platforms are logically sharing the same memory. I'm going to allocate memory for you to write into. You're going to allocate my half so I can write into it. So it's the model that basically portrays the ability to share memory across two distinct compute platforms for communications. So that's how the name came about. Yes.
I mean, you're saying that nothing has to change at an enterprise, network structure to do this, but they have to buy Rocky-capable cards, right? So there's only a couple of those providers, and it's not like people, when they make a choice to buy a 1 gigabit adapter, go out and en masse go buy RDMA-capable adapters. So how do you see that, all of a sudden now, everybody in their data center has RDMA-capable 10 gigabit or 40 gigabit adapters?
Yeah, so to repeat the question is, you portraying this as no hardware changes. Of course, every server has to have an RDMA-capable NIC. It is RDMA. It will require an RDMA-capable NIC. There are only a couple of vendors, I agree. But the reality is that in order to provide the technology, we need a provider that provides that solution and does it very efficiently. And the point is that, yeah, you're right. So what we would see in the data center is that it's not going to be very pervasive instantly. It's going to be put on strategic nodes where the chit-chat is very heavy. And so then I think it'll basically move as necessary as the virtualization model supports the expansion. There are other things that will make it become more pervasive over time. But initially, you're right, you have to deploy the adapters and provision them where the payback is there from a business standpoint. But yes, there's no way of getting around the technology. Yes?
What is the API for the application? Is the RDMA-like, like the zero copy, or is this like a socket-like application, so that I would take a copy of the application and just a sub-layer?
Right, so I think I got it all. Let me just repeat and you tell me, but what does the I/O model look like in terms of copies and so forth? So basically the way this works is the stack provisions this memory and manages it and exchanges it, again, transparent to the application, but it's fundamentally targeting transactional workloads, which is important in this environment. And everything is a copy. And so the zero copy is something we have our eye on for streaming and bulk transfer in the future, but right now, for the message sizes that we are looking at with the static model, it's extremely efficient. We prototyped moving it. Moving it means you may have to touch the programming model of the application if it doesn't block. So with this model, from a socket call, you're returning back to that application immediately. So it does copy, but it basically is targeting small data moves or transactional workloads. For streaming workloads, it's also very efficient. I'm going to show you that performance here in just a moment. But the objective was really transactional workloads. It does copy on both sides to hide the semantics from the application. copies outbound, copies inbound. And basically, you can think of the model as the applications are reading and writing into this memory, and the adapters are doing all the network work. So it's very efficient because we're not exchanging our keys. It's a one-time setup, and because of that, you're building on the pervasiveness of the TCP connection, long-lived pipes. Okay, so that's the overview. That was the first part, and just the next topic was I wanted to look at. So we finally shipped something. So last year we shipped our first piece of this, and it's on System Z, our latest platform, the BC12 and EC12s that IBM announced last quarter of 13. And here I'm just highlighting the ROCE card that we introduced, the ROCE Express 10 gigabit adapter. So now our platform has the ability, and so we can talk to ourselves. That's interesting. So we need to get a little farther, and that's the reason we're, again, here we'd like to be able to work with the community and work with the OpenFabrics Alliance to get there. But certainly, in order to provide an enterprise commercial-based solution, we need other platforms to support it. That's why we have the RFC that's basically an open solution. But this is our card that we announced in the fall. So it does require the latest machine in this card. So here's a guy telling you there's no hardware, but suddenly you have to buy a machine, you have to buy an adapter. But that's what we introduced last year. We also introduced software, of course, in our last release of ZOS. All of this was just released in the end of 2013. Now here's kind of the elevator spiel of what this is all about. The machine. So over on the left, let's talk about that for a minute. On the left, again, in the top left corner, there's this number with 80%, and of course everyone has to put a footnote next to any numbers, and it has the fine print underneath, and you cannot read that, of course. But the point is, you can imagine what it says, that your mileage may vary, etc. It has all the typical disclaimers. But at the end of this, I'm going to give you all the details. But the numbers on the left-hand side here are micro benchmarks, round-trip measurements from the application level, round-trip in terms of micro benchmark with no back-end logic. I'm going to give you macro benchmarks, real benchmarks in a moment. But basically, when we take something like a netperf, and we test this technology against TCP/IP, we see up to an 80% throughput improvement in transaction rate. And again, I'll demonstrate that in just a minute. Now, macro benchmarks are not going to see that. This is what the technology provides. That's the opportunity. And then, of course, real workloads will have think time and have compute time, et cetera, and it shrinks back down. But they will get a significant piece of this depending on their network traffic pattern. And just below that, we talk about the benefits for bulk data. In bulk data, we see throughput improvements depending on a number of variables of up to 60%. But what's more important to our customers is the CPU savings. And there we're seeing 50 to 60% CPU savings on both ends, the sender or receiver or the client or the server. And that one is really an eye catcher. So even though we were targeting transactional, we still see savings there. Again, these are micro benchmarks, and the real benchmarks are coming here in just a moment. And then on the right, we talked about what we announced. The ZOS that provides the SMC-R stack 2.1. We provide ZVM support for PCI direct attach on System Z. And we also provided a new hardware adapter to provide RDMA capabilities. Again, all of that introduced at the end of 13. Now, so here's a micro benchmark for ZOS performance. Again, this is just a little bit more detail. You have access to all this information because I'm going to give you a link at the end, but I can't cover this in detail because there's dozens of these charts. But I just really wanted to give you a sound bite of what this looks like. And really what you'll see is that the way this chart reads is request response is the pattern, basically 32 bytes out, 32 bytes back, and the number in parentheses is the number of connections, and the payload size is to the right. So it's RR10 means 10 concurrent connections, for example, exchanging a 1K buffer. RR10 connections exchanging a 4K buffer. So this whole notion of what large and small varies depending on who you're talking to. But the point is you'll notice that in here from a transactional standpoint is kind of the sweet spot. But what's interesting is where you see that this is order of magnitude is 700, 400. These are pretty big numbers. This is relative to Ethernet TCP/IP on our platform. And we know when we use TCP/IP, there are dozens of knobs to get the best TCP/IP and the best Ethernet. But nevertheless, I'm not going to go into all the knobs here. And you'll have access to that information. But the point is that you'll see that from a micro benchmark standpoint, that there's CPU savings on both ends, and the throughput from just a pure transaction rate from a micro benchmark standpoint are very compelling. And so now then you have to put real workloads on there, and the skeptics will want to see, well, okay, then what does the RDMA provide for a real workload? And of course, we have some of that, but again, there are many variables, and we understand that. But I think the point is that this chart demonstrates the capability of RDMA technology. And it also shows the capabilities of this model. Permanent memory, read right into, and let the adapters take care of all the data movement. So again, as we move out to the right and that blue bar starts shrinking, we start seeing things like, this is a 9 gigabit, and as we get out to the right, all the way to that blue bar, we're all the way out to about 16, 17 gigabit. This is a 10 gigabit link. That's both directions. So if it's 9, it's about 4.5 both directions, because this is request response with the same size. And again, this is all relative to TCP/IP using standard Ethernet. And as we move to the right, we start approaching line speed and saturating the line. So the difference, well, it's only 100% difference, but that's significant. We eventually get down to about 50%. But it starts looking like streaming or bulk data as you get farther to the right with these larger payload sizes. And as you get out there, the difference in TCP/IP is smaller, but it is you'll see that it's more of a CPU story. And that's what that balloon was telling you. To the right, we start seeing the CPU savings. Here are the real workloads, the macro benchmarks. And I won't spend a lot of time on them because you have a link to them. But up on top, this is a very interesting one right here. This is a client from Linux on X attaching to ZOS WAS Liberty, which is our light footprint of our WebSphere app server, talking to a backend DB2. And for this comparison, all we did was, again, change that from Ethernet to SMC-R, and we see something like on the order of a 40% reduction in what the client sees. So for this workload, this trade light workload, which is real workloads, real benchmarks, work on top of application middleware, that it typically makes 5 JDBC calls to the backend. That's a Java-based implementation. And when we replace those 5 calls back with SMC-R, the client sees about a 40% savings in terms of 40% faster. The one right below it is a file transfer. This is a binary put. Again, this is back to the 50% savings in CPU. The next example is CICS is our transactional application middleware for System Z. Just about every banking institution, insurance corporations use CICS. But basically, they have a distributed programming model where if you get into one of our clusters, the CICS will talk to each other. In this example, we again compared Ethernet to ROCE, and we see a 48% reduction in response time. So the real workloads are seeing, instead of 80%, they're seeing 40, 50% improvements. And then finally, the last example I provided down here was for WebSphere MQ. This is for the SOA implementation on System Z, where the applications will distribute the work between themselves using message queuing. And once again, with replacing Ethernet between the two of them, we see a 200% savings in terms of transaction rates of what MQ can do. So all of these are very compelling. There are many more of them out there in this deck that I'll give you. And there are the details, which is in the fine print here. There's additional details in the references I'll give you. What are we doing on Linux? So it's basically, we're in the process of developing this solution. We've been testing it quite a bit of time on Linux. It's intended to be a kernel-based solution. We cannot provide the qualities of services with a user space solution. It's just not possible. With the failover and the link bonding and the various solutions, the security solutions that we needed a kernel solution. So we're working towards upstream acceptance. I don't know if that'll be possible, but we certainly are optimistic. We hope so. We believe it's a very compelling solution. The intent is, of course, to share the technology and not require any license, anything special. It would be licensed under GPL. On System Z, we do not have a new address family. The kernel solution is in our kernel. Here we would introduce a transparent address family that it would just switch out and use the SMC stack if it negotiated SMC. If it did not, it would fall back and use the traditional IP stack. So you'd use the parallel stack for SMC if the rendezvous was successful. So under the covers, it would introduce a new, instead of AFINet, AFFSMC to use that stack. Again, it's intended to use existing BSD sockets interface. The application, again, does not change or is aware of this. It would conform to the specifications that RFC that we've distributed. Again, bullet 3 is very important. Even in this environment, we have to provide all those requirements that I described earlier. The kernel solution is what allows us to do this Q-pair sharing, link bonding, link groups, memory management, fork, link groups technology itself, all the solutions that are hard to solve in user space that applications require. If you can get into the kernel to provide that, then you can provide this solution. The Java enablement will be native. We'll have that as well. And again, from a usability standpoint, it's from an administrator standpoint, it's basically just enable it. Just turn the function on, and you can control the granularity, but you would not change your IP topology or provision IP addresses, etc. Linux, we've been testing this for quite some time, ZOS to Linux and Linux to Linux, etc. And we've been doing various interoperability testing. Our objective is to post the code this summer from our Boblingen lab in Germany is working on this solution, and that's their objective, is to get that out so that we can start getting some feedback. Here is an early look at the Linux numbers for testing Linux itself. Again, this is Linux compared to base TCP/IP to Ethernet. And without going into them, because I know I'm running over on time, is that you'll see, again, that the differences are very similar. There are some differences in what the ZOS numbers showed, but the overall pattern is very similar in terms of there's a sweet spot in the middle for transactional workloads that provide significant opportunity in terms of throughput and CPU. Again, I'm just showing an interactive workload, but as the object sizes get larger, the advantages shift to CPU savings. It's the same statement from ZOS, so the patterns are basically the same. Here's some notes about what we compared, what we ran. Again, you'll have a link to all this information so that I know you'll have questions about what was the comparison. This URL provides a web page that has several references, everything from security to performance information to detailed overviews to high-level overviews, YouTube videos, etc., to explain this in a little bit slower pace so that you can get some of this. And so that one will have several valuable links. It will also explain the performance information that I just showed you. And I'll be around for a couple more days if you'd like to have questions or if you have some additional information. So, anything else or questions? Yes?
When the packet is lost, for example, who is the person thinking just it is the ROCE? This is ROCE implementation inside the cards. So just how do you handle, for example, when you lost some packets?
Loss of packets?
Yes.
Well, so on the RDMA side, the loss of packets is handled by the adapter. So basically, we only use reliably connected Q pairs, and we use the advantage of our CQPs for this transmission. So software is not involved with transmission at all. It's all hardware, and that's basically, it really just looks like two applications communicating in memory, and the operating system is not involved with the communication, how the bytes get from one side of the memory buffer to the other. So retransmission is up to the adapters to handle that. Yes?
How do you handle the buffer advertising? Do you handle it or do you let the verbs handle it?
How do I handle the buffer? I'm sorry?
For example, you have set aside some memory
Right.
on one end, at the receiver end,
Yes?
where the sender can send. Now, after the sender has sent some buffers, this memory will get exhausted, right? Don't you need to replenish?
Okay. Right. So how do you resupply? So I promise you that I glossed over a lot of this, and I would be willing to talk to you. But the buffer, the intention is that we provision memory that's based on the socket semantics, which is TCP receive side. So whatever receive size is, we'll like double that, for example, and it's a wrapping buffer. So it just wraps. And and it's intended that the next piece would be an element that would be allocated to the next TCP connection. So it's a wrapping model. We never allocate anything more for that connection. It's based on a permanent, pervasive TCP connection. And so the buffer that's allocated for this connection wraps.
But if the receiver doesn't utilize that,
If it doesn't consume the data, how do I block the sender? So basically, we do have control flows that essentially knows that the buffer is wrapped, and the sender will basically block if necessary. Now, he will queue to a certain amount. That's tunable, how much you allow us to queue. But the point is our intent is to keep the block full. And for streaming workloads, that buffer is very large. And for interactive workloads, we almost never wrap because basically the pattern's request response. And so you don't block for the transactional workloads, very rarely. Yes?
Just a quick question. You said this is going to go upstream kernel within summer. Is this going to live under the OpenFabrics branch, or is this kind of on its own sitting as part of a, I don't know, in some other?
Right. So yeah. So the question is packaging and where's it going to go? So our intent is to post the code, get the feedback from the open source maintainers, but we did not have an intention to package with OFED. Just get into the kernel to make it common and work from there from both SUSE and Red Hat, assuming it's accepted into the base kernel. But if anyone has any ideas about how this could be packaged in a better manner, I'm certainly willing to listen to that. But our intent was just to put it in the kernel for code acceptance. Okay, thank you.